Kleiber's law above relates the basal metabolic rate B measured in kilocalories per day of an animal to its body mass M measured in kilograms. If the body mass of an elephant is 10 to the sixth times that of a mouse, which of the following best compares their basal metabolic rates? All right, so let's think about this a little bit. So let's just say B sub lowercase m, that the basal metabolic rate of a mouse, well, that's going to be equal to 70 times the body mass of a mouse. That's why I wrote the subscript lowercase m for mouse to the 0.75. Now, based on that, what's going to be the basal metabolic rate of an elephant? Well, the basal metabolic rate of the elephant is going to be 70 times, I could write the mass of an elephant to the 0.75 power, but we know that the mass of an elephant is 10 to the sixth times that of a mouse. So instead of writing the mass of an elephant right over here, I could instead write 10 to the sixth times the mass of a mouse to the 0.75 power. And once again, I don't want this notation to confuse you. Since I'm referring to B for a mouse and B for an elephant, I'm using these subscripts to differentiate. This is the basal metabolic rate for a mouse. This is the basal metabolic rate for an elephant. This is the body mass of a mouse. This is the body mass of an elephant, which is 10 to the sixth times that of a mouse. I could have over here, this is the same thing as the mass of an elephant. We know that the mass of the elephant is 10 to the sixth times that of a mouse. And the reason why I did that is once you write it this way, we can now express this in terms of the basal metabolic rate of a mouse. What am I talking about? Well, let's use a little bit of exponent properties to rewrite this. So this is going to be equal to 70, and then all of this stuff in that I am squaring off in green. Well, if I have the product of two things raised to an exponent, that's the same thing as raising each of these to an exponent and then taking the products. So it's going to be 70 times 10 to the sixth to the 0.75 times the mass of a mouse to the 0.75. And now I can rearrange it. This is going to be equal to, stay true to the colors, 70 times the mass of a mouse to the 0.75 power, and then you're going to have this thing times, so 10 to the 6th to the 0.75 power. If I raise something to an exponent and then raise that to an exponent, that's just like raising the 10 to the product of 6 times 0.75. So what's 6 times 0.75? Let's see, that is going to be 4.5. One way to think about it, that's going to be 3/4 of 6. So 0.75 is 3/4. So 6 times 3 over 4 is going to be 18 over 4, which is the same thing as 4.5. So raising 10 to the 6th power and then raising that to the 0.75, that's the same thing as raising 10 to the 4.5 power. Now, why is this interesting? Well, this part of the expression right over here is the basal metabolic rate of the mouse. So this is equal to the basal metabolic rate of the mouse times 10 to the 4.5. So we were able to show, just like that, is that the basal metabolic rate of an elephant is 10 to the 4.5 times the basal metabolic rate of the mouse. So let's see if any of these choices say that. The basal metabolic rate of an elephant is 0.75 times that of a mouse. No, it's 10 to the 4.5 times that of a mouse. So let's rule that one out. The basal metabolic rate of the mouse is 10 to the 4.5 times that of an elephant. Nope, doesn't make any sense. Because this is saying the mouse has a higher metabolic rate, basal metabolic rate, in terms of how many kilocalories per day it burns. You wouldn't have to do any math to just say this seems crazy, that a mouse would burn more calories than an elephant. The basal metabolic rate of an elephant is 10 to the 4.5 times that of a mouse. Well, that's exactly what we came up with. The basal metabolic rate of an elephant is 10 to the 6 times that of a mouse. And we already know that that's not going to be the case. Now, another way that you could have tackled it is you could have just looked at this. You could have just looked at this and said, okay, look, if I increase m by 10 to the 6th, if I increase it by a factor of 10 to the 6th, I'm going to increase b not by a factor of 10 to the 6th, but by a factor of 10 to the 6th to the 0.75. To the 0.75, and 10 to the 6th to the 0.75 is the same thing as 10 to the 6th times 0.75, which is equal to 10 to the 4.5 power, which we have right over here. So these first two you could have actually probably knocked out just off of a little bit of deductive reasoning, and even this last one to some degree, because you could say, look, if I increase this by a certain factor, because I'm raising this to an exponent, the basal metabolic rate won't increase directly by that same factor. So, but either way, we were able to figure it out exactly as well.